Alright, so in this video we are going to solve another problem from Flensberg, and this problem is problem 2.2, and it is saying that use variational principle to argue that although the equation 2.43, and what is that we will see in a moment, is not exact near the energy minimum density Rs equal to Rs star equal to 4.83, the result E star by N equal to minus 1.29 electron volt nevertheless ensures the stability of the electron gas. So we need to show that electron gas will be stable for this particular R value, and so equation 2.43 is nothing but E by N is E0 by N plus E1 by N, and that is equal to 2.211 by Rs square minus 0.916 by Rs, and this is Rydberg. So here this first part comes from the non-interacting electron gas, non-interacting electron gas, and this part comes from interacting part, the exchange, from the exchange interaction. It is because of due to the Coulomb repulsion between the electrons, the fact that no true electron can occupy the same position in the space, which is also due to the Pauli principle, is kind of gives this exchange interaction, this Coulomb repulsion between the electrons, and this comes from that, and it is, we determine this term using the first order perturbation theory. Okay, so now we need to use the variational principle argument and show that this indeed, so earlier if this term was not there, only this term was positive, and then it will not be, there will not be, this configuration will not be stable. But if we add this term comes with a negative sign. So if we just do del Rs of this E by del Rs of E by N, that will in turn give us a particular value of Rs for which this E by N will turn out to be negative, and that value is nothing but which is given 4.83. so for that value we will get our E by N to be equal to minus 0.095 Rydberg, and which is nothing but 1.29 electron volt, which is given in the question. So by just try to minimizing the energy, we can find this particular Rs, and for that we can show that this energy, we can indeed get a minimum energy, okay, for this configuration. And if not there was any this Coulomb repulsion between the electrons, then it would not be able to find a stable configuration for this system, and then there will require some external confinement potential to hold the electron gas in the gallium together. But for here the Coulomb repulsion is supplying that need and generating a stable configuration, and this Coulomb repulsion we calculate using the first order perturbation theory. We can calculate this term, and so this problem is something about that. So that's what they asking, that is not near the energy minimum density, the result nevertheless is the stability of the electron gas. So that's how it ensures the stability of the electron gas. So what actually happens is, generally when there is not, this term is not there, that means the kinetic energy is winning. There is too much kinetic energy between the electrons, of the electrons. But once we turn on this term, this exchange interaction, then that means that there will be some repulsion between the electrons. So the how far one electron travel due to its kinetic energy, that will be restricted. Okay, because there will be repulsion between the electrons also. So that force will restrict the kinetic energy, how far a electron can travel freely. In the free electron non-interacting case, free electron gas, they can travel anywhere at all the electrons. But once we turn on this repulsion between the electrons, then their kinetic energy is restricted. Okay, and by that we get this stable configuration. So it is because of this logic that we can get a stable configuration and at E by n minus 1.29 eV. Nevertheless, in spite of the fact that is not, this equation is not exact. Okay, I hope this is helpful. Thank you.